Hello, everyone. Welcome to today's Smart Safety Connection seminar. My name is Chun-Sung Hwang, and I'm a Safety in Transportation Fellow for Safety 21, a US DOT University Transportation Center. The Smart Safety Connection Seminar Series is sponsored by Safety 21 as an opportunity for faculty to showcase their current transportation project. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note the session is being recorded and all participants' microphones are muted. If you are joining us online, please send your questions through the chat, or if you are here with us in person, feel free to raise your hand at any time. You do not need to wait until the end of the presentation to ask your questions. You are welcome to ask them throughout. Now, I'd like to introduce today's speaker. Levent Guvenc received a PhD in mechanical engineering from Ohio State University, Columbus in 1992. He is currently a professor in the Department of Mechanical and Aerospace Engineering with a joint appointment in the Electrical and Computer Engineering Department of Ohio State University and is the co-director of the Automated Driving Lab. His current research interests include connected and autonomous driving, cooperative mobility of road vehicles, automotive control, and mechatronics and applied robot control. Please help me welcome Levent Guvenc as he shares his presentation, Vehicle in Virtual Environment Method for Developing and Evaluating Vulnerable Road User Safety of Connected Autonomous Driving.
Thank you for the introduction, and let me share my screen. So my name is Levent Guvenc, and I will be talking about the safety of vulnerable road users. And this presentation is on a project that's being conducted together with Professor Birin Aksun Güvenç from the Automated Driving Lab at the Ohio State University. And this is the research team. You can see me in the bottom right-hand side. You can see Professor Birin Aksun Güvenç on the left. And then the two PhD students, the main PhD student, Hao-Chong Chen, and the PhD student, Xin-Chen Cao, who's helping Hao-Chong in this work. Let me start by talking very briefly about the Automated Driving Lab. This is the main lab for autonomy and connected vehicles research at the Ohio State University. And we build our own research platforms. We build simulation models for automated driving, and you see an example that we did for the Smart Columbus project, which was the Smart City Challenge winner many years ago of the US Department of Transportation. And along with that work, we started building this vehicle in virtual environment method, which I'll talk about also in this presentation. We built hardware in the loop simulation systems like this one, which are innovative in that we add things like real traffic signal controllers, real onboard units, real roadside units, electronic horizon units, and the like into our simulations. We can actually play back real connected vehicles data or simulated connected vehicles data and insert our own connected and autonomous driving research vehicle inside that information and sense that information. And there were a lot of graduate students and postdoctoral students, as you see some of them in the picture, and most of them are working either in the academia or in the industry. And accordingly, our work has been, funded mostly by the industry and also federal sources. So let me start with the motivation for today's talk. Vulnerable road users and vehicles, they share the road. We all share the road together. We have to improve our mobility, but there's a problem. Unfortunately, the injury and fatality rates of pedestrians and bicyclists has been in an increasing trend in the US for a long time. There are similar statistics worldwide. So people are working, researchers are working on trying to actually improve the situation. And as you see right here, the trend has been increasing. There was a slight decrease based on preliminary data from 2023, but the decrease was not enough. And we definitely want this decreasing trend to continue and at a much faster pace. So what can we do about this? And NHTSA, National Highway Traffic Safety Association, has of course been posing the same question, and they've been analyzing crash data, and they've built this fatality analysis reporting system, FARS crash scenarios. On the left-hand side, you see the main causes of pedestrian crashes, and on the right-hand side, the main causes of bicyclist crashes. So the first thing we did in our two projects that are related to this talk for the Safety 21 UTC were to actually create these scenarios in simulation settings such that we can actually simulate them and then use them for development and testing cases for our vulnerable road user safety algorithm. So we mostly concentrate on the pedestrian ones until now, and we have started working on the bicyclist ones in our second year project, which is the one that is current. So if we take a look at what is available today, well, pedestrian and bicyclist injuries and fatalities are increasing. And autonomous vehicles were seen many years ago, maybe decades ago, as maybe at least a decade ago, as the solution that as we had more autonomous vehicles, more autonomy, since the driver error would be taken out of the loop, that these kinds of accidents would not occur. But unfortunately, that has not been the case. So more has to be done. And basically, our vehicles actually come with some kind of emergency braking system. They have radar camera that can detect pedestrians or bicyclists. But there are still cases in which these sensing capabilities do not work too well. So the question was, what can we do on top of what is available to help in reducing or improving, let's say, the safety of vulnerable road users? So one problem was non-line of sight or reduced visibility conditions, where basically those available sensors do not help you too much. And it turns out that these are usually a large percentage of crashes that result in fatalities. So one idea is to maybe on top of the sensors that are already available in your car, add some kind of communication capability like vehicle to vulnerable road user communication, and then use that to your advantage to understand where the pedestrian or bicyclist is, or either warn the driver or warn the vehicle such that it could do a better job of braking or braking assisting. So this was the idea. Instead of trying to come up with new infrastructure, new ways of doing this, since almost everyone has a smartphone, use a smartphone, the smartphone of the pedestrian or bicyclist, and maybe use the one of the driver for the communication such that results can be achieved right away. So here's the idea. You have your pedestrian, the pedestrian smartphone, and the corresponding smartphone of the driver in the vehicle. They communicate, in this instance, over Bluetooth. But the ideas I'm going to talk about are agnostic of the communication method. We also tried cellular communication. We added, the colleagues we work with added modems to the infrastructure like the traffic light, and then broadcasted the information from the pedestrian phone, which increased range. We also wrote directly to cloud servers and then read from cloud servers. It turns out that all of these methods work fine. The latencies are not big enough to affect performance. So basically, this communication between vulnerable road users and vehicles is not a bad idea. Then we need to somehow predict the path of the pedestrian or bicyclist, especially for pedestrians. This is a little bit tricky, whereas for the vehicle, we usually know what the vehicle is going to do. So based on that communication and computations, we send either warnings to the driver such that the vehicle can do comfortable braking. And then to be able to do this, to be able to send the warnings at the correct time, or to be able to do emergency braking more naturalistically, we take a look at real-world data for analysis of interactions between vulnerable road users and cars. So let me go back to this Bluetooth idea. For the experiments, we used an Android phone, and we did a lot of experiments with different methods. Instead of just using this rather recent Bluetooth 5.x technology, which is much faster, we also looked at older Bluetooth because not everyone is going to have the latest kind of smartphone. And it turns out that even if the pedestrian or bicyclist is actually placing the smartphone in his or her pocket, which reduces range, obviously, the numbers, the numerical values are not bad. And technology is improving, so basically, communication is not going to be that much of an issue. So here are some simple experiments to actually show that this idea could work. So on the left, you see a bicycle where the smartphone is docked, and you could do the same with e-scooters. Actually, we did that. You can actually dock it in the e-scooter, and then you actually fix the corresponding smartphone in the car. And this is where we did our own tests. This is a garage building where we keep some of our cars. This is an excellent place for creating a no line of sight with a vehicle and a vulnerable road user, such that only communication will help. So your LiDAR, radar, camera are not going to see what is coming. So that's when communication is needed. So at first, we used available connected vehicle applications like the intersection motion assist one, in which the vehicle obviously does not see the pedestrian that's going to appear from the left side of that building. And there is going to be a warning which you should see. And obviously a collision is going to be avoided. This is a non-line of sight case. Then you can also do line of sight cases at a larger distance, basically, where the bicyclist will be coming from a longer distance. Again, your sensors might have some difficulty because that bicyclist or pedestrian is going to be a long way away. Same intersection motion assist, scenario. Let me see. Sure, okay. So basically, it's the same scenario. You might barely see the bicyclist on the left corner, and then there is going to be the warning flashing. And if you don't want a warning, you can actually connect that warning to an emergency braking system. So that's the idea. So we did not want to just use existing algorithms. Those intersection motion assist algorithm is an existing algorithm from the connected vehicles database. We wanted to build our own algorithms. We also wanted to use some very basic learning control. So we had to collect data, and what best way than to use this smartphone right here. Either the pedestrian or bicyclist has it, or you can actually put it in the car, and that can be determined automatically. And it turns out that your phone has a ton of sensors, like a very good GPS sensor, IMU sensor, and other sensors, so you can collect data. This is an actual pedestrian moving around. And I use that data for later analysis and also for training neural networks if you want. So we decided to test both a Kalman filter and some very simple neural networks, long short-term memory networks, which turn out that most people are using them, especially for future motion prediction of pedestrians. And we used a 1 second ahead prediction and a 2 second ahead prediction. Why did we use such simple algorithms? Because we wanted to actually make sure that we could implement them in the smartphone. And for training the neural networks, even if they are simple, you need data. So some of the data we collect, we also created using programs like Wisdom or similar programs, synthetic data on pedestrian and bicyclist motion. So you see this on the right-hand side. Then we used our own program with our own graduate students to collect a lot of data that we could use for well, both training and validation of what we were doing. And this was not enough. We actually looked at publicly available data. And this is an example of publicly available data that we could readily use. This is what we call a smart intersection in a city called Marysville, which is very close to our main campus of the Ohio State University. There are 4 cameras. It could be radar or LiDAR also that take a look at all the oncoming traffic, including vulnerable road users, analyze the motion, and then send broadcast basic safety messages corresponding to all of these. So we could either go there and we did this, listen to this broadcast with our car, collect the data. And then it turned out that the city had actually collected about 9 months of data, which was made publicly available. And then we decided to actually analyze data. Obviously, 9 months of connected vehicles data, that's a lot of data, 24 hours a day for 9 months. So we had to write some semi-automatic or automatic tools to actually extract the close vehicle and vulnerable road user interactions. So this is from August, this is from September, and these are the areas where this vulnerable road user and, well, vehicle interactions are taking place, the ones that are close enough, well, close to being dangerous. Obviously, no accidents happened during that time frame. And then we decided to analyze the data. So we actually drew these data on these plots where we have vehicle time to zone and pedestrian time to zone. These mean that the intersection is the zone, the critical zone. If the pedestrian and the vehicle are at the same time, meaning the origin at the zone, that means they're either colliding or they're just almost on top of each other. So basically, you need to be away from this range. And if you actually plot the data like this, it looks like garbage, but if you use heat maps, you'll find out that most people, most drivers, actually give about 2 seconds of time gap when they see a pedestrian close to an interaction. Close to an intersection. So this is naturalistic data. This tells us how actual drivers like to behave, which is, well, more cautious drivers, which is the majority of drivers. And if you are to build a driver warning system, or if you are to build a system that will actually do automatic brake and steering, we have to use something like this. We should not really be closer than this to pedestrians. So the next step is you need to actually predict the future motion of pedestrians such that you can make those calculations ahead of time. And there is ground truth data. This blue plot right here is actual pedestrian data. And the algorithms, the neural networks, the Kalman filter that we are testing here, they don't really know the future of the data. They are just using the past data. And usually in straight portions of this, it's very easy to predict the future path. It's the parts where the pedestrian is changing direction, where the difficulty arises. And this seems to be doing a satisfactory job. Obviously, there are going to be some errors when you are doing those turns, but eventually, in a short time, this catches up. So that part of the work made sense. We also said, instead of only doing motion prediction, let's try to take a look at behavior or intent prediction. This is one method. We tried lots of different methods. It's like, what is the pedestrian trying to do at the next instance? So we used, of course, our ground truth, and our confidence levels were pretty good when we trained our neural network based on that also. So this is how a driver warning system can be structured, and then obviously can be used for automated braking and automated braking and steering. This is the zone where there could be a collision between a pedestrian and a vehicle. So basically, first you need to be aware that there's a pedestrian that's moving in that direction, which would be around here. And if you, well, this region, around here, you need to inform the vehicle that something is going on, and of course the driver, and it would correspond to this point in this pedestrian time to zone, vehicle time to zone graph. And the time to zone is how much time you have into that collision zone. And eventually at that point, you have to actually fully brake the vehicle such that your interaction is a safe zone and not in one of these areas, definitely not in the red zone where you have to apply emergency braking. So the idea is to make sure that you are completely safe and you don't really need to revert to emergency braking. If obviously these fail, then you need to do emergency braking and maybe emergency braking and steering. And this is how we simulate. You actually see that this point of interaction moves towards the origin as the vehicle and the pedestrian move. But then right at that point where they're almost on top of each other, the vehicle stops. So basically you move out of this zone right here. And I'm showing this program because this is how we analyzed also real data. So we did have access to 2 days of tryouts along with all the data we had, where there were 6 vehicles, about a large number of pedestrians, bicyclists, scooters, driving around all the time. And then, yes, we were able to take a look at all the problems with the approach. And to be able to do a good job, basically, you also need to put some safety margins. Basically, what's happening as the pedestrian and vehicles are approaching an intersection or a crosswalk is that you actually move along this path. Someone has to do something, which is usually braking and steering, so the vehicle will brake steer, and you will end up here without going into these dangerous zones right here. So that's the idea. And of course, this was implemented. We were working with a major automotive OEM at the time, and of course, being a major OEM, they were able to put all these warnings, etc., in the dashboard. We are a university, which this is not possible for us. So what we did is we took a heads-up display, and we put the smartphone in the vehicle such that we could show the informal warn zones, and the computations were taken care of in the smartphone for this instance. So this is one of the demonstrations where you see the heads-up display. In the videos, it doesn't show very well. That's where we try to show. So it starts blinking and it changes color. It warns that there is a pedestrian coming from. There's a pedestrian coming from the non-line of sight place right across the building there. Same with 2 different views. And of course, you have to note that these are a little bit dangerous. Obviously, we know what's going to happen, but you have to be careful in doing things like this. And here you see the data analysis and the different warnings that are being sent as this experiment is taking place. And of course, you see the end of the experiment also. But if you want to continue with this, obviously, you'll note this is for a bicyclist case, that the bicyclist, the pedestrian, and the vehicle, they're coming pretty close to each other. So I have a couple other videos where we can see the same thing at intersections, real intersections in the university. And obviously, the vehicle is stopping. Of course, the pedestrian does not really want to jump in front of the car because of safety reasons. And then this is a similar demonstration at this is a more commonly used road at Ohio State University. And this is the interaction. So the question is, well, we don't want to just do warnings. We want to take a look at braking, and steering. And even for these warnings, we want to come up with safer interactions, especially if you want to experiment. So if you want to develop in a safe environment, the first part is we start with model-in-the-loop simulations, which is, of course, what we do most of the time. Then we build hardware-in-the-loop simulation setups like this one, where we also have communication between the vulnerable road user and the car in real time happening in this system. We try to add realistic traffic, which is also safe. And then the next level is, well, it's not very safe to actually put the pedestrian in front of the vehicle at all times. It's not very safe to do a couple of test runs in a proving ground and then just to deploy technology in real life situations like a lot of companies are doing. We should do something in between. That's the vehicle in virtual environment method that I started during the beginning of my talk. So this is what the method is about. This is on developing and testing or demonstrating connected and autonomous vehicle technology in a safe manner. We actually take our vehicle, put it in a proving ground, empty area, or in our case, in a large parking lot, which is empty. And then we cut off all the sensor feeds. It's as if this vehicle has extended reality or virtual reality glasses, because we run in real time a simulation, a realistic simulation of driving in a replica of the real world. This one right here is the Linden area in Columbus where autonomous shuttles were operating. And then basically all the feeds that go to your computers are from the virtual environment. The computer calculates the drive-by-wire commands, and then the vehicle moves in that environment. So basically, if you want to do this, we need to make sure that however much you move in the virtual environment and your real motions are the same. So the vehicle in the test actually thinks it is driving in this environment, whereas it's in a parking lot, and you see that in this case, the parking lot had vehicles. In the virtual environment, it's actually overtaking a vehicle, as you see in the bottom right corner. And but in the parking lot, it's not, it's just empty. And of course, this was an OSU, Ohio State University parking lot with vehicles. We usually go to another parking lot with very large flat areas, so we don't really see other cars. And it turns out after we did all the coordinate transformations and so on, how much we move in the virtual world and how much we move in the real world are very nicely synchronized. And then basically, once you do this, you can do manual driving on the left, you can do autonomous driving on the right, and you can get sensor feeds from the virtual environment like camera, LiDAR, or other virtual feeds. So how is this going to help us? That method was developed for basically developing, evaluating, and demonstrating connected and autonomous driving algorithms before public road deployment, and then where you could actually take a look at critical situations, like cars jumping in front of you and so on. So the way this could help is you can actually have multiple users. Like this is your car. That's a user sharing the same virtual environment. And this is your pedestrian or bicyclist. You can even have other cars. They actually communicate their location information to the simulation, which is running in real time, such that this vehicle corresponds to the motion of this car. The pedestrian motion is given by the real pedestrian. And there is no possibility of physical collision because they're at separate locations, usually close by, but they don't need to be. They can be physically separated. They can be communicating through other means. But realistically, in the virtual environment, there's going to be a collision risk. So here you can even collide virtually, whereas nothing happens in the real world. And this is the method we are applying. So basically, your real pedestrian and your real vehicle are doing real motion somewhere else. You actually sync the motions, do frame transformations such that your virtual pedestrian and virtual vehicle are in any of basically the farce cases, the 10 cases, the 5 pedestrian cases, and the 5 bicyclist cases that I showed you in the beginning, such that we can realistically do this and implement this in our car, where we do all the computations that's right in the computers in the car. And then this is a simple demonstration of how this might look like. So the graduate student who is working in the project, he is actually walking behind the car, whereas in the simulation, you will see that he's actually walking in front of the car. This shows that basically we can do these kinds of interactions easily. So next point, we do have automatic emergency braking in cars. So 90% of today's light vehicles already have this, but this is not good enough. This is very basic. And NHTSA also showed this, the government found out about this, and then they said, well, we want to make things safer. So they came up with this new or revised version of the standard, which is going to be mandated by the year 2029. So first thing, you have to detect vulnerable road users better. So pedestrians and cyclists, there are problems with determination of where they are, detection and tracking. So even under low visibility or nighttime driving, you should be able to detect. The next thing is the speeds have been increased. So for collisions with cars up to 90 miles per hour, for collisions with pedestrians up to 45 miles per hour. I think I remember them correctly. So the speeds are much higher, and these have to perform much better than the ones that exist. So this is a requirement because we want to reduce the number of accidents, and this is how we actually test these automated braking systems using dummies in track, improving grounds. So we'll continue doing this, but then we need better sensing of vulnerable road users. So basically, if you have communication capability on top of your LiDAR radar camera, that's going to be useful. And then automatic emergency braking is not going to be enough. So this is not part of the standard, but yes, in some situations, we should actually steer out of the collision, so that green path. And in actual practice, you don't even need to fulfill that full steering trajectory. It would suffice to actually do part of it. So slow down and then just veer a little bit away from the pedestrian or bicyclist such that contact is avoided, and then you can stop here. So this much is enough. So basically, your collision avoidance methods should concentrate on braking plus steering. And our lab has been doing a lot of work on these technologies for a long time. Collision avoidance systems for vulnerable road users. So Professor Aksun Güvenç in our group, she's been working on this elastic band method for a long time. This is based on the potential field approach that was borrowed from mobile robotics. So you actually think of your path as a band like this, which you deform in case you have an obstacle. And then you can try to do this more optimally. And other people have used things like support vector machines, etc. And then neural networks, reinforcement learning or deep reinforcement learning. And this part is what we are currently doing in our first and second year. Well, we finished the first year, but in our second year UTC project. So along with that, we are also taking a look at more classical approaches, which have to do with, well, how do we follow the path? So in reinforcement learning, this is done automatic, but with other methods which are used for benchmarking, how do we actually, once we find out the path that is deformed, how do we follow it? So we use what's called a disturbance observer or model regulator, which actually rejects the curvature of the path, which means we follow the path very accurately. And on top of this, we add a feedback controller, which we design using parameter space methods. So this approach has worked well. And then here you see trajectories. Difficult to see because of the shadow of the buildings, but there's a red trajectory which shows a collision avoidance path with an obstacle. This is the exaggerated view. And on the right-hand side, you actually see what happens if we have different amounts of communication delay. This could be communication plus computational delay. And well, the performance is not very bad. So this is also what we're taking a look at. What if, well, we're not under ideal situations in practical implementations? Are we still going to be able to do that? And the other approach, the main approach of our UTC Safety 21 project is applying these reinforcement learning algorithms. So basically, you see the reinforcement learning algorithm here with this deep reinforcement learning implementation. The vehicle is not just trying to stop, but it's also trying to actually pass the pedestrian. And of course, after training the network, this is the pedestrian time to zone. This is the vehicle time to zone. Obviously, we don't want to be here. We don't even want to get into these regions right here. Definitely not this emergency region. So once the vehicle starts, it's going to steer and brake until there is no possibility of contact with the pedestrian. It will have overtaken the pedestrian safely. So all of these have been published recently. And then this is a preview of our proposed next year project. And Professor Levent Guvenc and our students have started working on this already. So this one uses control diaphragm functions, control barrier functions for the basic motions. And there's a higher level deep reinforcement learning approach that tells you where you want to go. Once this is determined for one step, and this is made in steps, then the CLF-CBF approach tries to find a safe trajectory, the safe controls that will actually get you to the next point without any collision risk. And this is how it's done. And there are some preliminary results, and this has also been published very recently with static vulnerable road use, how the path is changing, and with dynamic vulnerable road users. So this takes me to my last slide. This is what we're trying to do, and we are one research group who's working on this and approaching the problem in many different ways. But basically, we went this curve to keep going down because we need to improve the mobility of everyone, pedestrians, bicyclists, scooters, kids, elderly people who are going to be in traffic, and they want to be using, well, they want to be walking, they want to be using their bicycles, but they will be interacting with cars, especially at intersections. So we want to make sure that they are safe, that the number of fatalities goes to zero, that's vision zero, such that people will not be discouraged from using these, well, healthy choices of mobility like bicycling and walking. And a lot of people are working on this. Vision Zero, Columbus has one. Every state, every city has one of these Vision Zero approaches. There are a lot of things you can do, and using connectivity and automation to do things in the car such that the car is safe for in its interactions with vulnerable road users is basically the research problem we are taking a look at. And of course, there's a lot to be done, but we all have to approach it. This should be the main goal. So this ends the presentation. These are the contact information, and then I'll stop at this slide right here.
Thank you, Levent. We actually have a really nice crowd here today, so I'm going to open it up for questions. Does anybody have a question that they want to ask? Go ahead. And go ahead.
Okay. So, can you hear me?
Can you hear us okay, Levent?
Yes, but can you speak a bit louder? My speaker is at its max end.
No problem.
Okay, I'll try. So, I think I understand the principle that this is to basically improve some kind of detection on the vehicle itself, right? But I also thinking that could this be reversed into a way to detect a close call collision and then work backward to be like a data collection, and then
Yes.
that could inform people who design the street to make the street safer based on the location that they detect any close call that they got from your system.
Yes, I think you are, if I understand correctly, because the sound is a little bit faint on my side. Yes, this can be used for data collection. And later the data can be used. Of course, privacy issues, I said, that being separate, for making these interactions safer. Yes, it can be used for that purpose. It's interesting that our phone has all those capabilities, and you can even use it to collect vehicle dynamics data from your car. Did I understand your question correctly, or?
Yes, that is my question. And do you see any things that would be like, I think we can say that it can do that, but do you also see any like problems or some issues that you could encounter when doing that?
Well, there are a lot of issues. regarding the use of communication between these phones. So it would be best to actually use it to complement what's available. So we have to enhance our algorithms with cameras, lidars, radars, what have you, and then first use this information on top, which is very useful for 9 of set. But then in real experiments, we realize that if you have errors in localization, sometimes you have false negatives, sometimes you have false positives. So we had to work a lot on these, but these are solvable. So yes, anytime there is real data with errors, error accumulation, there might be false positives and false negatives, which are both not very good. But the thing is, we worked a lot on such data, and this is correctable. And when we come to things like, well, braking, steering the vehicle, emergency braking, emergency steering, we have to be careful. So all well, our main priority should be to make sure that we never get into that situation. Because for the occupants of the vehicle, it's not a very nice experience when your vehicle suddenly brakes and then brakes and steers, and it's not a very nice experience for the pedestrians who are around also. When you're trying to suddenly brake and steer, you have to think of the following vehicles and vehicles on the other lanes. And of course, people are working on these. Obviously, our algorithms can take care of these. And then the last part, when you take a look at algorithms like learning algorithms like reinforcement learning, of course, well, they are trained on data. So the problem is, what if you encounter situations that you've not encountered before? That's where this vehicle in virtual environment method could be very useful, because we can actually import those into the environment and test before real deployment. So there are other issues, of course, but these are the ones I can think of. And of course, with learning methods, sometimes the steering oscillates. So you have to take care of things like that and basically fine tune these before, well, real world use. Did I answer all your questions?
Oh, yeah.
Hi. No, I just wanted to ask, how far is the investigation or the experiment to be put into reality, or like to be using more cars around all the streets and yeah. That.
So basically, automatic emergency braking is in your cars. So, and sometimes it does funny things. Sometimes it actually brakes when it's not supposed to brake, which is not very good. So it is a system that definitely needs to be improved. Sometimes it sees pedestrians, sometimes it doesn't. And the times in which it doesn't detect the pedestrian is like a very easy case, so you don't even understand. But this is a deployable technology. And the company actually we were working with wanted to put this in series production in all these cars, so something happened. Economy went bad. I don't know what. Well, the automotive industry is not doing very well right now, so they're not really going in the direction of, well, what is not needed unless it's mandated. So we see the fact that NHTSA, the government, is going to put this mandate by 2029, a very positive sign, because, well, people are trying to, automotive companies, suppliers, researchers like us, we will have to work on improving these methods such that they are deployable. So I say we are pretty close to deployable, better performing deployable products. But then the automotive industry will try to get extensions, waivers, and so on, saying it's too expensive for them and the like. But I'm hopeful that within the next 5 years, or 2029 is 5 years, we are going to have much better automatic emergency braking in cars. Now, braking and steering, when that's going to be implemented, I'm not sure. It's going to probably take longer.
Okay.
I have a question. So I think this is a really interesting experimental concept. I'm wondering what your personal thoughts are about personal responsibility for vulnerable road users, especially with the interest from the manufacturers. I'm wondering if we're moving towards a scenario where pedestrians have the responsibility to be visible on the street, to not move erratically, and to potentially carry devices with them in order to not be hit by cars.
Yes.
So what's your personal thought about responsibility for those users?
So that's thank you. That's a difficult question. So personally, obviously, I think everyone is responsible. So you'll probably recall that there were instances where very low speed autonomous shuttles were hit by pedestrians because the pedestrian was taking a look at the smartphone, didn't even notice, just hit the car. Nothing happened, obviously, but yeah, these kinds of things could happen. And then we see a lot of vulnerable road users, especially in the US, where I live. People don't even look at the road because they assume that the vehicles are going to stop automatically, especially in a crosswalk. So there is responsibility on everyone. I don't know. I cannot talk about the legal responsibilities, but basically, if you make a system like this mandatory, there will be some legal responsibilities for the vehicle manufacturers. But then again, obviously, as pedestrians, bicyclists, we also have to make sure that we check the road and then we are more visible. And as bicyclists, we have to make sure that we actually are obeying the rules of traffic and so on. So from a personal point of view, I think there's a lot that vulnerable road users should also do. But then there's also a more vulnerable part of vulnerable road users like elderly people, people with vision impairments, etc. That's where the car software is important. You need to make sure that you understand what's going on. So that's a very difficult question, but I think there is, for me personally, there is a lot of responsibility on the manufacturers. But then equally, there is a responsibility on the vulnerable road users. You should not jump in front of the street, but there are instances where this is going to happen. So
Thank you.
I don't know if it's satisfactory, but it's very difficult. We all, because legally it's different, but ethically we all have to be responsible in a shared environment like intersections, walkways, etc.
Thanks, Levent. I'm not sure if you're able to see it, but we actually have a question in the chat. So how much,
Check the chat.
no problem, I can read it out loud. How much do geolocated priors affect your VUR detection and decision process? For example, are the weighting factors favoring detection made higher in areas with crosswalks rather than on interstates?
So that question I can answer. If you take a look at the FARS scenarios, you will see that most of these, pedestrian or bicyclist involving crashes have happened in urban areas. So not on highways, but there is one FARS scenario for a highway use. So that's also possible. But I would say this would need to be weighed more towards intersections where school zones are, in low speed zones, etc. As far as highways are concerned, I think automotive companies, because their cars are used on highways a lot, have done a good job of improving the safety situation in highways, so they are going to continue that. But what we need, the improvements we need are in urban areas, especially in walkways, controlled or uncontrolled stop sign controlled intersections, and school zones. Those are where we have to be careful. And residential areas where there are kids. So that's when you have to maybe boost up your sensors and make sure that the algorithm works best. And of course, work zones. I forgot about that. There's a highway situation, work zones.
Thank you. I have another question in the room.
Kind of as a follow-up to that question, well, a lot of the urban areas in the United States, at least, are suburbs with wider roads and relatively high speed limits, ranging from like 30 to maybe 45 miles per hour. So that's kind of a interesting in between case of lower speed streets and highways. And those suburban roads usually have like less like crossings, and the street grid is less dense. So there is a problem where sometimes people cross in the middle of the block because the block is simply too big. Could this technology be applied in those scenarios, and how would that be different from compared to like a denser and lower speed environment?
So to answer your question, I think driver warnings will be useful, but not good enough, because in those situations, you don't really expect any close interaction, because they are rare instances, which means it should be an automatic system. And yes, in that case, this kind of an approach would make sense. So along with your usual perception sensors, which should work if there was also communication using the smartphones, then we would be able to know about that rare instance very easy. So the car should be listening and trying to see if there is an interaction all the time. And in those cases, an automatic braking would be more suitable, because the driver would not expect that, and we have reaction times sometimes up to a couple seconds. Sometimes we don't even cognitively recognize the dangerous situation until after it's over. So in those cases, I would recommend using definitely an automatic system to help.
Thank you.
Are there any other questions? Okay.
Thank you, Levent, for sharing
Thank
your
you.
work. And then thank you to all of today's attendees for joining us. Today's presentation will be posted on the Safety 21 website, What's Happening page, along with a link to the video of the session. For students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transportation enthusiasts. Thank you for attending our Smart Safety Connection seminar, and we hope you will be able to join us again for our next session. In the meantime, please feel free to contact us with any questions. Thank you.
Thank you.